if you are here for the Visual AI in Manufacturing webinar with Voxel 51. My name is Nick Lotz, and I am here to talk about uh, how visual AI, and I'd say proper visual AI practices can help power adaptive process control. So this is a themed webinar. It is going to focus on data-centric AI and how it can be used to train and evaluate models, really focused though on manufacturing NPC. As a point of terminology, I've been having to catch myself in my practice runs of this. You'll hear me use model predictive control and adaptive process control a little bit interchangeably. I think they're fairly similar, but one is really a subset of the other, so apologize in advance. But thank you all for those who have joined so far. It looks like we have a solid group of folks. I am going to go ahead and get started. And if more folks trickle in, that is totally fine. So um, just as a point of order, as we go through the webinar, feel free to ask questions at any time using the Q&A panel. Chat is available as well, but I would encourage you to use the Q&A. It's a little bit easier for me to kind of address and filter that way a little bit. Um, but that said, we'll go ahead and get started. So a little bit about me. My name is Nick Lotz. I am with the company Voxel 51. We developed the 51 platform, which is used to curate and train and manage data sets predominantly used in computer vision models. What's a little bit near and dear to my heart is my background is actually in the physical sciences, more specifically chemical engineering. That was my training. Kind of got my start in more traditional manufacturing and process control type environments. I realized that I liked air-conditioned offices a little more than factory floors. And so I've been working in the software, DevOps, kind of full stack development fields for quite a bit of time now. I'm based in Nashville, Tennessee, so it is currently 11:03 a.m. and quite cloudy outside from the vantage point of my home office. And when I'm not, hacking away at my keyboard, I try to do the absolute opposite in my free time, which is go and hike around with my pet Labrador, preferably visiting as many national parks as I can. So, thank you all for being here. I'm excited to lead today's webinar. Give me one more second here to get a sense of who we've got, and I think we are good to go. All right. So who is this talk for? Really, if you're involved, I would say if you're involved in any part of the Venn diagram of machine learning, particularly visual AI and manufacturing, as we'll see pretty quickly, there is quite a deal of overlap between verticals when it comes to adaptive process control. The types of problems you solve with MPC or model predictive control has applications well beyond just manufacturing. So if you have a data science background, a manufacturing engineer background, if you're a machine learning practitioner, if you're an ops leader or an operations, this is for you. Really, the goal of this is to go through a workflow of data-centric AI. How do we build and curate the multimodal visual data sets needed for kind of next-gen manufacturing practices? The focus is really going to be, again, on the adaptive control part of manufacturing. I think the anomaly detection is a pretty mature field at this stage. There's certainly a lot of extra work that can be done there, but really what we want to do is be proactive about how we train and deploy models that actually take corrective action in order to, maximize whatever your objectives are, maximize yield, reduce defect percentage, reduce waste, increase efficiency and training iteration time, whatever it might be. All right. So here's where we're going. We have a lot to cover in a pretty short amount of time. There'll be some slideware as I lay out concepts. You might notice I have a couple tabs open in my web browser as well. I will be showing quite a few demonstrations to again, this is visual AI, so it helps to have those demonstrations. Something I would encourage, and I actually neglected to put this on one of the beginning slides, so I'll put it here in chat, is one of the data sets that I will be using is accessible in our demo environment. That is a web-based environment that is open to folks here on the call, anyone who wants to access it. So it's called try.51.ai. It does require registration. You do need to create an account on it, a free account, but an account all the same. And when you log in for the first time, the kind of welcome modal that will be shown to you, the very first one is the MV Tech manufacturing data set. And that'll be one of those data sets that are going to be involved in this talk. So mostly if you want to explore the 51 platform in a way that doesn't require you to like download the Python package and start organizing local data sets yourself, that's one way you can do so. I'm going to be in a more kind of fleshed out demo environment that I'll be using for some of these workflows. So where are we going? We're going to start with why data-centric visual AI. Really, the goal here is to kind of set the standard of how much of an effect data has on model performance, both what we might call kind of ad hoc machine learning models and ones that are integrated with control systems. So once we establish that motivation, the next core piece is going to be building visual data sets. Sensor streams produce massive amounts of data, terabytes, if not petabytes or more. How do we manage those? How do we visualize them? How do we balance them? How do we use, frankly, the minimum amount of data needed to train effective models? So that'll go into this building aspect as well as curating for quality. That has to do with both data set balance, data that actually has a positive effect on the controller, such that we're making corrections that are giving us the result we want. That includes data that ensures lack of bias, as well as data that ensures that we're meeting like safety and compliance standards as well in terms of representation. And then we'll move towards the model training loop. How do we evaluate industrial models? And how do we iterate on that evaluation? A really important aspect here is going to be called scenario mining. When we have, especially in multimodal data sets, it can be difficult to drill into the actual conditions, particularly among time series data that can cause models to fail. So that'll be part of what we drill into. And then finally, we'll close the loop. The very nature of process control is that it's iterative and you're hopefully improving the controller over time. And we'll finally tie that in to measuring impact. How effective are we at actually creating and deploying models, and importantly, having visibility into what we build? So I want to start with a little bit of motivation. I'm not going to spend too terribly much time on this. If you have been around and if you've seen any content produced by Voxel 51 before, you'll be familiar with this motivation. If you haven't, really one of the guiding principles of the way we think about visual AI and really AI in general is that data is key. So sorry, there's a little bit of a glitch here in the top right. And forgive a little bit of the marketing speak on this slide. I promise there won't be too much of it, but ultimately data is responsible, we find more so these days than pure model architecture to determining whether your AI applications succeed or fail. Massively successful vision language models, foundation models, they can always be improved. But as Mr. Satya Nadella of Microsoft says, there's a trend toward models being commoditized. And one of the ways we see that trend is the fact that so many open weight models are being produced that are really state of the art. And that tells us that, again, improvements can always be made. They happen every month. But at the same time, the core value is your data. And we see that at a technical level as well, where whether your models succeed or fail is very much often less so the model architecture, very much more so whether your data reflects real world conditions, is properly balanced, whether there's enough of it, and whether it is, again, balanced in a way where your model is being trained properly and not failing in the long tail. And there's a lot of examples of this. Again, I'm going to go quickly here, but we've seen them all over the news, whether it's safety critical or not. Self-driving cars failing to see stop signs, misinterpreting a pedestrian as a motorcycle, so misjudging the speed, um, uh, not being e-commerce and retail stores not being able to handle the full representation of behavior in the store. And again, what we end up with is we have models that are like 95% accurate or 98% accurate, but that final few percent, um, tweaking the model architecture doesn't get us there. It really comes down to data issues. All right. And there's a few reasons why. Visual data, especially, has a lot of work that has to go into making sure it is processed and ready to be trained on. LLMs, right, are to an extent self-documenting and self-annotated, right? Models that are trained off text data are trained off the text patterns themselves. Visual data needs to be annotated for the most part, and it's hard. That's hard to annotate and validate at scale. Requires massive amounts historically of human labor to draw bounding boxes and fill in segmentation masks. And it's also very hard to debug. When the ground truth is wrong, um, that's like that's like finding a needle in a haystack, especially when it comes to false negatives, right? If there are labels missing on things that should be labeled, especially that can be almost possible to debug outside massive amounts of human QA. Historically, foundation models are starting to change that. Um, there's also a lot of integration issues, especially when it comes to process control, right? Process control is heavily reliant on time series data. That is making sure that the various scenes, sensors, streams, all the different data modalities are all captured and snapshot at a very particular point in time. And the ability to analyze and train on all that data at a very particular point in time is paramount. Um, I would argue that self-driving modalities in the automotive space have advanced quite a lot over the past decade or so. In a lot of ways, manufacturing still has a lot of work to do, which is a cool opportunity, but also a challenge. Right. Give me one moment here. Okay. And part of the reason too is if you're an engineer that works with data, um, the standardized tool ecosystem is still fledgling in a lot of ways. We're working to change that with here at Voxel 51 by having a very robust, almost an IDE for your visual data development. But a lot of tools are still homegrown, and having worked with homegrown tools, it's really a pain. Um, you're talking like mounted NFS shares of like local data that you need to mine through with like a file explorer and using custom scripts to try and pull out things. There's a lot of shared spreadsheets. Versioning exists, but is sometimes not utilized to its fullest potential. And the reality is the larger your data set, has become important for building better models, it's really difficult to debug data without kind of a nice unified interface to see everything in front of you and start performing quantitative metrics on that data and making strategic changes to that data set so it leads to better models. It's very, very difficult to scale the current suite of homegrown tools because, and I've kind of mentioned this earlier, garbage in leads to garbage out. Um, when you don't have good insight into your data, when the ground truth is wrong, so model metrics are misleading because of it, And that's what's referred to silently degrading model performance here. Your models will fail in the real world, but you simply don't know why. Um, Models themselves, especially given current architectures, are in a lot of ways a black box. You don't want your data to be a black box too. So here is where um, 51 comes in. So 51 has a couple core attributes to it. It is a predominantly visual data management platform, though we do support audio and a couple other pieces of unstructured data as well. It is designed for curation, annotation, and evaluation of your data sets, with model training and evaluation being a core part of that as well. The fundamental philosophy is your data sets are side by side with any type of machine learning work that you do. There is an open source distribution of 51. It is available as a Python library that you can pip install. We at Voxel 51 also make available an enterprise version that is hosted. It's a client server model. And it also hooks into a lot of kind of integrations at scale, like GPU clusters, your data lake, cloud storage, wherever you might stream in data, as well as your training networks, model registry, and so on. So open source 51 is really, really powerful for individual developers. Our enterprise edition is designed for large teams that are working at scale. But really, the feature set here is held in common between the two. Inspect, manage, and curate your data. I'll say in the enterprise version, even though we have a plugin as well for the open source version, annotation using foundation models to give us a first path at labeling, and then finally model evaluation metrics. Yes, Amit, real quick. That is the open source repository that I just put there in chat. All right, so ultimately, the goal here is to be extremely iterative in building a successful data pipeline. So I have this very elegant little chart here that I threw together using my clip art skills. And the idea here is you can't curate, annotate, and evaluate just once. That gives you a first path. It's just like any type of software development or engineering, for the most part, you need to continuously improve, whether it's in manufacturing, whether it's in software, or whether it's in machine learning. And notice even annotation is still here in the middle. And that often kind of brings up a lot of questions where you're like, well, if we're annotating ground truth, shouldn't that be like our source of truth? The answer is yes, but human annotators aren't perfect. If you augment human annotation with annotation using foundation models, then that can have an extremely positive effect on your efficiency loop, because models can work very fast, and then you can QA with humans and still end up with high quality labels that you can feed into model training. Right. So what does it mean to build visual data sets, especially from a manufacturing perspective? So historically, computer vision in manufacturing was very focused on anomaly detection. We're talking about like the overhead camera that's shining down on a machine and taking a picture of the object as it goes through the line, and then if you're using machine learning models, it'll be evaluated against these, or it'll be run against these objects, and we're hopefully detecting defects, whether it's using object bounding boxes or segmentation masks, and then we're using that to evaluate our yield. The issue with that is that um, ultimately that doesn't help us when it comes to in the loop process control. It gives us an after the fact view of what some of the latest output of our product was, but it doesn't allow us to make corrections in real time. The real challenge here is connecting vision data so that production lines can adjust automatically. Anyone that has an engineering or physics background knows that process control is in even nonlinear process control is, time is always going to be an independent variable. right? So when data is time series, you need to map that to the visual data that you stream in. And this is largely what traditional visual AI might look like. So what I'm showing here is a screenshot of the 51 app. This shows what's a very common manufacturing data set called MV-Tech. It is an anomaly detection data set. It's very powerful. It's useful, well, powerful as far as data sets go. It's useful for training models. It's a benchmark data set for manufacturing. And it does, its purpose, like just about any anomaly-based data set, is it's good at indicating if something went wrong. It's less so indicating where, why, and how. Now, it's correct in terms of where, in terms of like where on the product. It's less clear about where in terms of where on the production line and in what condition, under which conditions it went wrong, especially in single modality data sets like this. Now, there's still a lot of utility here, right? So if I go to this tab here, this is the MV-Tech data set. This is this traditional overhead view of of products. Within 51, you can perform all sorts of curation, like for example, sort, filter, slice, dice data. So for example, I might go in and organize my view by um, data category. And then I can easily visualize things like prediction masks um, and defects. So right here, if I look at this model that evaluated it, or sorry, if I look at even the ground truth, let's see if I get anything here. Let's see if I can find anything here. Yeah, so we can see some predicted anomalies here using one of the models. And then we also have classifications of whether a given product might be normal or defective. This is all well and good, but again, this tells us more of the what than the where or the how. What I mentioned before that's critical is time series data. So ultimately, data needs to accurately reflect a snapshot of production at a given time. And this is a bit of a process change in manufacturing that, as I mentioned before, automotive has, due to its very nature, has spent a lot of time kind of making progress in over the past 10 years or so. In manufacturing, there's still a lot of work to do. In fact, I'm actually not aware of a real benchmark manufacturing data set that includes multimodal time series type data. There's some synthetic ones out there. I know eye candies is one of them, which is a little bit more of a synthetic, not a toy data set, but close to that. And there's certainly like 3D manufacturing data sets. There's a 3D variant of MV-Tech, but the multimodal cross sensor uh, or multi-sensor consolidation with a timestamp is really what manufacturing needs. So if you look at this example here on the right, this is actually not a manufacturing data set. This is a data set called new scenes. This format in 51 is called a grouped data set. So just like you can open a sample here, and this is MV-Tech, and you see a single image, this is the same modal. However, we have multiple views here. On the right is LiDAR, which is a common sensor in automotive. And then we see multiple camera views. In manufacturing, you might include either fields within the sample or simply heat maps of things like temperature and pressure and so on. Over here on the right are label fields. And one of the critical aspect here is time series data. So there's a timestamp field here in the middle right. It might be a little bit small to see on your screen, but the idea here is that all of these samples are mapped to the timestamp. As you gather data in 51, it's extremely straightforward to add your own custom fields. So as you stream in data, you can perform um, so this is the 51 Python library. You can easily add fields and metadata to your samples, including both visual data and notice numeric fields like in this case temperature, pressure, speed, and so forth. And here, we have a timestamp, for example, that gets added as its own field. So the accumulation of this is what's called a grouped data set in 51. And again, there aren't a lot of benchmark manufacturing group data sets out there, but the way new scenes works in 51 is if I go to the new scenes data set, is there's several helpful visual cues. So purely from a browsing and curation standpoint, um, the prominent tile here that you can see in the grid, you can change between camera views. You might show the LiDAR view, and that allows you to slice and dice and filter based on that view from the left-hand side here. What you can also do is open up a view, and oh, for some reason, LiDAR isn't showing up here. I can actually open a different data set in a minute that shows that. But here we can see the different views that match a particular um, point in time. So t is the independent variable here. Let me jump to one other real quick. There's another one called Kitty, which is another self-driving data set. Oh, you know what? There might be an issue with LiDAR rendering in this demo environment right now. I wish there wasn't. It would be nice to see. But anyway, LiDAR appears here. Sorry about that. Um, but that being said, what that means is that from a data standpoint, in the database, you have common samples where, again, the independent variable is time. And when you're training on that, you can ensure that there's consistent views that are being trained on by the model. And then the presence of physical metadata is critical here, like temperature, pressure, speed. That gives us a full view of what the surrounding conditions are. Okay, so getting into the guts of things a little bit. Um, Multi-view data and multimodal data, whether it's 3D point clouds, LiDAR, multi-image, even video. So I haven't mentioned this, but we do support video in 51, both tracking data sets and just frame by frame. Where do data sets live? Well, your local computer isn't a good option, especially when we're talking about multimodal data sets, because the scale of them is just too large. And this infrastructure question, even though it's not always top of mind, is critically important because generally your data sets that you're actually training models off of is going to be a subset of like your total data, your total raw data. So we need to have access to that raw data as it gets streamed in so we can access it and import it if needed as data sets into whatever computer vision platform we're using. So just having like a local folder of data is not something that can scale very well. One option is what we call cloud-backed media. So this has been around for a while. You take all of your data, you throw it in an object store, and that becomes your source of truth for your data set. So 51 does do that out of the box. So if I actually click into a sample here and I look at the thumbnail path, this is actually a Google Cloud bucket that the data lives in. And if I wanted to import more samples, I can do so, maybe media and labels. I can select the format of the data set. So 51 has its own format, but there's also common formats for like say visual data sets like Cocoa and so forth. Again, multimodal data sets, things get a little more complicated. So there might need to be some custom curation there. But the data directory, you can browse your cloud environment and import new samples if needed. So from a purely object store perspective, that can be useful as like the source of truth of your unstructured data sets in terms of once they're curated, they live in the cloud. However, that doesn't address the um, the raw data question, right? Um, More frequently, we use data warehouse and data lake software to stream massive amounts of data. So we're talking the Databricks of the world, BigQuery, which is a Google product. And we need to be able to access that data somehow without like importing everything all at once. So we need strategies to take our curation and desire for balance and pull it from an outside source. Um, so data lake integration is performed through what's called data lens. This feature in 51 uses an operator framework that allows for extending the 51 platform to integrate with just about anything you want. So when you think of an operator, it's almost like a plugin, but I'd say um, even more extensible. The way you write operators to super simplify it is you use the 51 operator class, which can integrate with the 51 platform, pull in the SDK of whatever your data lake is, and create rules around how that data lake gets queried and map them to samples in 51. So this example here in Python on the left is showing how we're importing 51 operators and the Databricks, or 51 libraries and the Databricks SDK. And over here on the right, we are defining attributes for how we interact and query our data in Databricks. And the end result is something like this. So this interface here called data lens is shown here is based on how we define this operator. So there is a little bit of coding work that you'd have to do, but at the same time, it gives you full flexibility of how you want to query your data lake and preview samples that can then be imported into 51. So so this is something that would be coded up by the operator. Now, some of it might be like a series of classes, right? Like literally checkboxes. Like I want this type of product under these conditions that have been like tagged or labeled in our data lake already. However, that's not always the case, right? Like often your data lake doesn't have that level of like metadata. Increasingly, data lakes like Databricks and others are introducing vector search and natural language search. Um, so that allows you to like search using natural language and to find data that might need to be added to your data set for balance purposes, or you're realizing that's become a model failure mode. So we need to find how we can augment our data set with more of this data, whatever it might be. So if I search for, this is actually going to be another outdoor condition data set. So this isn't directly a manufacturing one, but the same principle holds. If I say like wet conditions, and then I search, in a moment, we should see a set of tiles show up that matches the approximation of that natural language search. And then there's an import button we can use to actually import that data. So we'll wait just a moment here. And again, this is outdoor data here, so this is not manufacturing data. But again, you can kind of see the gray and wet conditions here. And then if I wanted to, I could click import data. I can choose to import a certain amount that matches those number of samples, that matches that conditions, or all samples matching the parameters. I can choose to add custom tags to it. And again, this is a way where I can augment my existing data set that lives in a cloud object store with additional samples from like a large data warehouse. So if we're talking about like massive amounts of data being streamed in from sensors, that would be where it likely lives. But then I can actually augment my data set without having to like plop every petabyte of streaming data I have into a reservoir that we're trying to train models of. That's not reasonable. All right. So when it comes to data curation, especially at scale, we need proper access to data, and we need to be able to slice and dice it, and we need to be able to augment it as appropriate. And again, multimodality is key. We need to be able to map data to time series because we can't actually go through a proper process control loop without that. All right. So how do we then train and evaluate models for MPC? So MPC stands for Model Predictive Control. It's adaptive process control can be considered a subset of that. Traditional model predictive control is more deterministic equations. So when I was in school, when we took our control theory segments, and that was kind of an area of research for me as well, model predictive control at the time, especially in like traditional process engineering, was trying to figure out what was basically a giant system of ordinary differential equations, um, and develop models based off of that. And then those models would be predictive signals to the controller, which would then adjust in anticipation of new conditions versus like feedback or feed forward or traditional feedback feed forward controllers or even traditional nonlinear process control. So increasingly, though, MPC is using AI models, right? Because you can ultimately, what matters is that the model that is put in the box is as effective as possible, whether it is equations or physical hybrid models or pure like deep learning models doesn't really matter in this extent that we're really going toward performance. However, we need to figure out why models need improved in the first place. And when you use deep learning models, they can be a bit of a black box because it's not like you're debugging against series of a large system of equations. You don't have as there are techniques, but you just don't have as much insight into model weights the way you would like traditional ODEs or PDEs. So often you need to look at the data to figure out why a model might be broken. So one example is imagine a model that is like detecting like holes in the ground. Well, in reality, that might be caused by conditions that are like shadows, right? In a manufacturing context, a non-defective sample could have a shadow cast over it that a model interpreted as defective. The root is actually defective data, not a defective model. Similarly, imagine a situation, this is in retail, so not directly manufacturing, but imagine a situation where everyone is wearing like coats in the store, and then the model suddenly predicts that there's a massive amount of shoplifting. Well, in reality, it might just be wintertime, um, and lots of people are wearing coats. Likewise, in manufacturing data sets, we need to have an understanding of surrounding conditions so that we know whether temperature, pressure, humidity, and so forth are having an effect on the actual visual output that the model is being trained on. And that's largely where data quality comes in. So data quality analysis allows us to kind of take a retroactive look at our data set and figure out what exactly is the current state of our data that might be biasing our model in some way. And generally, especially the benefit of manufacturing is that we have control over the environment, and we also have a desired outcome of what do our non-defective samples look like. Therefore, if we perform certain data quality computations and we get a histogram of like the extent of our extremes, we know we can easily identify whether our data set is balanced or not. So this is something that is available in the enterprise version of 51. And the reason it's in the enterprise version is because it requires like some connected GPUs to perform the computation. But if I exit out of here and I go into the data quality panel, and it's a good practice to put it side by side with your data set. I think the segmentation masks here are loading a little slow today. Here are several metrics that are like commonly used and can be helpful in understanding our data set distribution. So brightness, blurriness, aspect ratio, entropy or noise, and then near and exact duplicates. So for example, if I look at blurriness, here is like our distribution of samples, and we can see that there's a very long tail. And especially further along in the long tail, we can decide whether or not these might be having an effect on our models by figuring out which samples are in that long tail, and later, which I'll get to in a minute, figuring out whether those are responsible for things like maybe model confusion or simply false positives or false negatives within our model evaluation metrics. So for example, if I go here and I kind of highlight this longish, let me figure this out here, this longish tail, if this will let me slide, there we go. We can see whether or not like blurry samples actually show up as blurry or whether it's some other condition that's causing it to be calculated this way. This is taking a little while to load. I'm pretty sure it's the segmentation masks. Oh, well. And here we can see it's actually largely a product thing, right? So here we can see that like it looks like this carpet here is kind of showing up as a high degree of blurriness. But within that, we can also start to see, you might see kind of shading here and there that might start to give us some informative views as well. And because every sample has like a unique ID, what I could choose to do is I could choose to select these. There's also in the operations box, there's also a way you can select all samples in the view. And I could choose to save these current filters as a view, which I might call blurry samples or something like that. And again, that gives us kind of a set point from which I can perform additional model evaluation. More on that in a little bit. All right. So data quality can give us a good snapshot of what samples tend to be on our extremes with certain data quality metrics. Now, again, these data quality metrics do not tell us if they will bias the model, but if we are examining, particular model failure modes, they could give us information as to whether those same pieces of data might be responsible. And again, it gives us that kind of drag and select ability to create these views. So let's now go into the model evaluation side of things. Especially with visual data, there's always an element of both visual and quantitative analysis when it comes to model eval, especially when you're training multiple models. Because visual data failure modes are often tell you more of a visual story than even a quantitative story. And simply an F1 score might not be enough. You need to go further into the actual like conditions to say, okay, which subsets of data might have caused these failure modes. So let me go back to my model view here and open up the model eval panel. So there's a couple famous models used for anomaly detection that will pretend that these are my models that I trained, PADAM and PatchCore models. They've been evaluated both globally and against each category of product in this MVTech dataset. If I put it side by side with my data, I can click into a given evaluation, maybe this hazelnut one, and I can view evaluation metrics against this data set. What I can also do is I can view them side by side with another model. So we have the PADAM evaluation, and we also have the PatchCore evaluation here. Now we can see already, just through this visual numeric analysis, that PatchCore has one, has better metrics in terms of accuracy, precision, recall, and F1 score. We can see the true positives, false positives, and false negative numbers, which of course are contributions to the F1 score. We can see metric performance in terms of precision and recall, and then its harmonic mean, which is going to be the same, which turns out are the same in this case. But where we can really dig in is we can start to see things like class performance and confusion matrices. So for example, in the confusion matrices here, we can see where PADAM misclassified normal versus anomalous products versus the PatchCore model. And that tells us that tells us what we can drill into for this particular product. So for example, if I click here, we can see that, and I click into one of these samples, we can see that the ground truth suggests it's an anomaly, but where's the PADAM? The PADAM model incorrectly classified it as normal. And we can see the entire distribution of this. And I'm realizing now I did this with the hazelnuts instead of the carpet example from earlier. But if we go back to data quality metrics, we can also see whether these same samples match the view that we generated from data quality. But model evaluation metrics alone like this might not be quite enough. Scenario mining is also important so that we can understand what underlying conditions, especially in if we consider different fields like temperature, pressure, and so on. So this scenario analysis tab allows us to create custom conditions that basically creates a custom view and gives us model evaluation metrics based off that view. So for example, let me try something else here. Uh, oh, sorry. Let's actually go back here. I want to go into I'll go into the toothbrush data set. Why not? So here's the toothbrush data set. I'm comparing it with the patch core toothbrush evaluation. And we can see they are actually equal. So let's do something else here. We'll go back and do hazelnut. All right. So here we can see that we have the PETA model in orange and the patch core model in blue. And we see the distributions of false positives, false negatives for each split, right? For both the training and test splits. In this case, we have one false positive in the training split. We have 19, sorry, what is it? Yes, false, sorry, one false positive in the training split, 19 false positives in the test split. That might not be, in the training split for the other model, and that might not be like representative balance in the actual test splits. So that's one way where we can start to see, okay, is our data properly represented and balanced in our splits? You can also start to identify things like data leakage, right? Is there anything in training that is like leaking into test that shouldn't be? In addition to that, we can see the confusion matrices. For some reason, confidence distribution isn't rendering here. I'm not entirely sure why. We can see the subset distribution of total samples. Where this gets really powerful is, again, this is just MV-Tech, but if we had a scenario analysis we can create, let's try this actually, a new scenario where if we had the sample fields for, say, temperature, pressure, humidity, and any type of surrounding data, we could choose that field, and that becomes the basis from which we're evaluating model performance. And again, that allows us to really, really take stock of surrounding conditions because we have those conditions recorded as metadata fields in the sample. So it's basically just something we're querying at this point. And that allows us, again, to think about how can we either change those conditions or augment our data set with better representation of those conditions. Lighting's a big one too. All right. So what do we do about this? We've basically come to the point where, okay, we have this data-centric platform where we can build visual data sets. I didn't go through the model training program here. We kind of assumed that we trained a model already and now we're evaluating it just for the sake of time. But 51 has deep integration with MLflow and the entire set of PyTorch libraries. And because we're extensible and we have like open source Python plugin ecosystem, we can in a pretty straightforward way integrate with almost any type of training framework. What do we then do? How do we measure impact? So I want to make an additional kind of emphasis on the predictive part of model predictive control. That is the linear flow is we have data, we train a model, we apply that to the controller. That gives us some kind of outcome, and that outcome generates new data. But that new data we then need to, augment into our data set in a balanced way. That kind of goes back to data lens, where we then retrain our model, and so on and so forth. Oops, sorry. Um, as we go through this, there's a couple areas of friction that we tend to encounter. Once again, one of those might be the ground truth, right? I kind of have glossed over the fact that ultimately the success of your models in visual AI is, unless you kind of do some advanced things with like unsupervised learning and things like that, ultimately you need some kind of ground truth as like a starting point for the most part. Again, foundation models here can become a big help with that in the sense that they can help offload the work of human annotators. So 51 does have a feature called auto labeling. That allows us to do what we might consider a first pass, that then can keep humans in the loop when it comes to labeling our data. So pretend that this is raw data that we maybe used, vector search to import from data lens. So I'm actually going to, this is technically our ground truth, this defect and defect mask fields, but pretend like those don't exist. We just have raw data and maybe IDs associated with them. Um, Auto labeling allows us to target all or some of our data and perform either classification, object detection, or instance segmentation on that data using foundation models. So for example, maybe, actually, let's do this. Maybe I'm going to open up that current view of blurry samples. What I can then do is I can choose a model, either classification or detection or instance segmentation. Um, Again, this is the MV Tech data set. So the way it's organized is there's normally classes of anomalies because it's an anomaly detection data set. The way we interpreted that here and kind of permutated it in this instant version of the data set is just like anomaly or no anomaly. So when using foundation models like this, you might actually want to have more like of a fixed set of anomalies that you are classifying against. You can again use detection or instance segmentation as well. And an anomaly detection data set like this would normally either be this or this. And from there, you can choose your model, either a zero shot, an open, or a fixed vocabulary model from a variety of state-of-the-art models. So for zero shot models, there's the OWL models, the YOLO world. Um, or maybe one like that. And there's a variety of fixed vocabulary models as well. So for example, if you're choosing a traditional YOLO model, there's a fixed selection of classes you could choose from, which aren't really relevant here in anomaly detection. But if you're performing a zero shot model, you might say something like, classes might be tear, burn, stain. You can also bring in your own models as well. Um, This example just includes some state-of-the-art foundation models in the list. And then really, really, really important is this settings field. So you might call it like auto label. What is this? BIT. You can select the mask output location, like the bucket paths that you're writing to. And then critically is setting a minimum confidence threshold. So because you're applying a model here, you need to basically select, hey, what's the minimum confidence threshold I'll accept? It can be really tempting to put in a very high confidence threshold. In reality, low to medium actually we found is what maximizes recall. So a value of like maybe like 0.35 or something like that. Um, does it give us some more false positives? Yes. But we make the argument that false positives are in general better than false negatives insofar as recall is maximized, because false negatives are very, very, very difficult to isolate and root out in large data sets. False positives are much easier because like there's the thing, it's wrong. Whereas a false negative is, it's basically a needle in the haystack. And then ultimately you would run this, it would run with a connected GPU and then give you a set of labels. So Going over real quick, I do have a model run staged up. It is against an automotive data set, but you can see an example here. So we call this verified auto labeling. And if we look at a label run, here we can see that in this example, what the auto labels, the auto labels that the foundation model, in this case, object detections, put. And even though I set a minimum confidence threshold, I can adjust it further. Like I can decide that, this low has way too many false positives. Maybe I can adjust here, and then I can see what labels are captured by this, and then the average confidence, and I can start to get a visual sense of things. Like, so for example, if my confidence was much lower, I might have like this, POV vehicle selected when I don't want it to, for example. And then the human in the loop side is you can add labels for approval. And that allows for additional human QA. So the reason I'm ending with that is it takes us back to the front of the loop of how do we actually ensure that our data and our ground truth are where they need to be in the first place. All right. So that being said, this is again the big takeaway. Um, Model predictive control and ADP isn't magic. It really just requires more work than traditional anomaly detection. The two big kickers are time series metadata and numeric like indicators of the environmental conditions as a function of time, and and again the multimodal streams that allow you to construct group data sets in 51. From there, the existing loops that you're familiar with of model training, evaluation metrics become a lot more manageable once you have that kind of data curation in place. And then there's some things that can speed you up, features that speed you up in the form of auto labeling with foundation models and human in the loop QA and so forth. So with that said, that finishes my spiel. Thank you very much. I'm now open for questions if there are any additional ones that you'd like to send through chat. So let's go ahead and address a few of the questions in chat so far. I think folks are in listen only mode, so it'd be difficult to get sound in. But if you're able to put your question in the Q&A or in chat, that would be helpful for me to address. The first one is from what looks like Lewis. If I'd like to curate audio and text data, does it make sense to convert it somehow to visual data and then analyze and convert it with 51? Can this be done? Okay, so we do support audio in the form of spectrograms, right? So the the visual equivalent of audio data would be a conversion to a spectrogram. In 51, we are working towards what we might call full audio support, but we do support it in the form of spectrograms in the sense that we support video files. And insofar as you can load a spectrogram as like an MP4 file, for example, then that can be imported as data in 51. Text data is still on the way. Um, um, there are methods out there that are kind of bleeding edge research in terms of converting text to like visual equivalents. That's largely what vector embeddings are, right? The interplay of like natural language and strings versus visual representations of them. At the same time, the level of support for that is still on the way, where we wouldn't call ourselves like kind of a text native machine learning tool quite yet. Next question, more logistics related. Will the recording be available? Yes, there'll be a follow-up email that includes your resources, including a link to the recording. And then from George, has anyone vibe coded a custom data lens successfully? Maybe a little bit of a rhetorical question. I can't tell, or it might be a serious question. So my recommendation is if we have a very active Discord community as well as our 51 operators repo on GitHub. If you're running into like issues with data lens connectors, which I want to be fully admitted is like hard. um, that's a tough problem. that, or it's a tough architecture to sometimes get right, feel free to like throw a question on Discord or open an issue on GitHub. We have I know our engineer, one of them, Tom, who's one of our key people that works on this, would love to like help out and just help improve it. All right, some of these questions are now in. Let me address a couple of these in chat. Um, how can this be applied to the oil industry and pipeline infrastructure for the oil industry? So my take is, this is near and dear to my heart as a chemical engineer by training. Process control is somewhat the same here. Things like temperature and pressure and thermodynamics in a lot of ways have visual equivalents in the form of heat map and time series data. Tools like Aspen Tech, which you might be familiar with in the oil industry, have been increasingly using AI-based model predictive control as well. The data set managed of it is still a problem, and this is where visual representations of it can still work very well. So my argument is, it will require a bit of work because a lot of this stuff isn't native to like multimodal visual data sets. But if it can be represented numerically as a function of time, my argument is it can be represented visually, and you can train models off of it. Feel free to hit us up on Discord, or I'm going to put my email in chat at the end of this as well. Feel free to carry on the conversation. I'd love to kind of ideate with you on that. Okay, if we have data of manufacturing parts available on the cloud, can I use it for predictive maintenance so that each customer can get the potential errors? So assuming it's in a cloud object store, yes. Because that can be imported to 51. If you're talking, let's see, if you're talking about, can I use it so that each customer can get the potential? If you're talking about model errors, that's just a matter of exporting your data, your model evaluation data from 51. If you're talking about the anomaly errors, that's a matter of exporting your data set from 51. And that's trivially easy. In 51 Enterprise, there's a big export button where you can export particular views, or it can be done in the 51 library as well. All right. Geospatial data. Yes, we do. There's one in the demo environment here. For example, let's see. We actually have a quick start data set that's available in our dataset zoo. If you go to the 51 docs, this is not quick start geo. I don't know why that's there. We do support geosystem data. Let's see. Yeah. To answer Jen's question, we both sell it and it's open source. We have a core open source library. We have a 51 enterprise platform as well. Okay, back to the Q&A section for a minute or so. How can visual heat maps combining model error, environmental errors, and time series data be used to proactively adjust MPC parameters, bridging AI model insight with traditional process control systems like Aspen Tech? So that's a very loaded question that I can't give you a full answer for here. Aspen Tech does have a pretty robust SDK and API. You're also able to load in models and create, PRD diagrams and MPC folks and MPC setups with it. The visual heat maps would be the data. The model error would be the evaluation metrics. So that part's done in 51. And then the actual simulation and experimentation, both simulated and real world, can be done in Aspen Tech. That's like the model deployment side and the model design side, or the system design side. So, it's ultimately just two applications that both have their APIs that you kind of learn to glue together, but it will require some, custom integrations. That's probably the best answer I can give at this time. All right. Yeah, couple next steps. When it comes to, I'd say for general like insight and feedback and stuff, our Discord is a great place to get connected. If you actually go to voxel51.com, all the way at the bottom here, it's kind of hard to find. There's a link to our Discord where you can join the community and sign up. So that's a great place to get connected. If you're interested in like I'm not going to spend much time on this, but if you're interested in like the purchase and procurement side, there is a book a demo button, but you will be going to sales folks at that point. So, ye be warned. And then finally, one thing I would encourage is that if you do want to play around more with either the open source library or the enterprise version, there is this try platform that you can use. There is also the open source repo that you can pip install from GitHub as well. All right. But with that being said, thanks again for your participation and all the great questions. We had a great group here. If there's anything else you'd like, also feel free to reach out to us on Discord, especially. Otherwise, have a great rest of your day.